Hello, my name is Indrek Must and this is Working with Modern Lab Equipment, Mechanoelectric Measurements. This course will give introduction to electrical measurement techniques, will introduce some modern electrical measurement instruments, and the special focus is on bioengineering applications, and also it is aimed for people working on bioengineering related field. Why do you need this kind of course? In your research career, you will come across with very different measurement instruments, which most of them have some element of electrical measurement technique implemented inside them. But in most cases, you're not exposed to the internals of these instruments at low level, and actually you're not supposed to. But in case you want to develop a technique on your own, or you want to debug the existing technique, you really need to understand more about the capabilities of these instruments. At the end of the course, you will be more familiar with the capabilities of modern electrical measurement instruments. You will be able to choose the instrument regarding your special needs of your technique. You will be able to read better the manual for the electrical measurement instruments and understand the important characteristics of these instruments. But this scope is very broad, so to narrow down, the case study is how to convert a mechanical input into an electrical output. Let me first introduce you to the instruments we will be using today. First, we have a common multimeter, that is Bremen BM257S. Then we have an oscilloscope, that is Rigol DS1054Z. And finally, we have a electrochemical workstation, that is Bioengineering BP300. Here we can see the input stage for this instrument, and this is actually converted via some cables to this box, which actually performs all the smartness. And all these instruments cover pretty well the very different ranges of instruments. And just to give you some more indication, let's consider the prices for these instruments. So the multimeter is at the range of €100. The oscilloscope is at the range of €350. And this electrochemical workstation, this particular one, is priced about €25,000. For our demonstrations today, I prepared a simple parallel plate capacitor. For this, I cut out a piece of printed circuit board. This is a double layer one. Consists of 2 layers of copper separated by a dielectric medium. And this dielectric medium has a commercial designation as FR4. This is the most common material for all the electronic circuit boards. And now this cutout piece forms a parallel plate capacitor, and we can directly calculate its capacitance using the well-known formula here. First, the geometry, the area and the distance between the plates we can directly measure on our sample. We also know the permittivity of vacuum, that's a constant. In addition, we need to know the relative permittivity of this dielectric material. And this is actually very straightforward in our case, because the 4 in this name directly equals to this relative permittivity. And I have already calculated this out for you. The capacitance of this parallel plate capacitor is 273 picofarads. Now, let's consider we want to measure a voltage across this capacitor. As simple as that. But before that, let's observe the output of these three instruments in case of no input, which is leads disconnected. First, let's take a look at our multimeter, which has its leads disconnected. And indeed, we read 0 volts, which is not unexpected, right? Next, let's take a look at our oscilloscope. This also has its input to the channel 1 disconnected. And on the screen we see a waveform. This is a periodic waveform with a frequency of 50 Hz. But let's keep that aside for a moment. Instead, let's take a look at our average value. And indeed, the mass function returns, it's jumping around, but it's around 200 microvolts. 200 microvolts, which is less than the resolution of this multimeter. So we can consider this also as very close to 0. But now let's take a look at our electrochemical workstation here. This also has the input leads disconnected. But we see that the voltage at the very moment is very close to 3 volts. It's about 2.75 volts at this very moment with the leads disconnected. Is this instrument broken? Or is there more to that? Let's find out. Let's now look at our voltage measurement problem in more detail. So let here be the inputs to our measurement instrument, whether it's an oscilloscope, a multimeter, or any other device. And this is the generalized depiction of our measurement instrument. Ideally, of course, when we want to measure voltage, we only need a voltmeter inside. So this will just return a voltage at our inputs. Perfect. But unfortunately, we are living in a non-ideal world. So each instrument is also characterized by a finite value for internal resistance and also a finite value for internal capacitance. And now, when we consider a measurement of open circuit voltage, that means a voltage with no input connected, the value which the instrument returns really depends a lot on the additional components to our circuit. Let's now find out what are the values for these components in case of all our instruments we considered. A common notation for input impedance is given as internal resistance Ri in parallel to internal capacitance Ci. So let's find out these values from the manuals. So here's our multimeter, and indeed we easily find for DC voltage the input impedance will be 10 megaohms in parallel to 50 picofarads. Okay, let's now move on to the oscilloscope. Oh no. Oh no. this is in Chinese. What shall we do? Okay, but luckily, in case of oscilloscope, we have the information we need right on the front panel. Here, we can read that all inputs are 1 megaohm in parallel to 13 picofarads. So let's write it down. And finally, let's take a look at our electrochemical workstation. And here, under the section electrometer, we find that the input impedance is, surprise, 1 teraohm. That is in parallel to typically 25 picofarads. That is in the case of a standard electrometer. But here we see we have installed a special low current probe that contains a more high quality electrometer. So we find the manual for that, and indeed in the manual for the low current probe will be 100 teraohms. In parallel to 6 picofarads. So clearly these values are different. And now let's turn back to our capacitor, shall we? So let's connect our oscilloscope to our input. Oh, and what we can see that the amplitude for our sinusoidal 50 Hz signal was much amplified. Let's do it one more time. This is disconnected and this is connected. Definitely a huge difference in the amplitude. So where does this 50 Hz signal come from? What we did here is that we connected a huge antenna as the input for the oscilloscope that receives all kinds of electromagnetic waves that are around us. And we are in the lab environment, so we have a lot of power cables that all transmit electromagnetic waves at the 50 Hz frequency. Let's now go to the dessert, shall we? So here we have our capacitor connected to the ultra-low current module of the electrochemical workstation. And this is the open circuit potential on this capacitor. And currently it reads 0.3 volts, so 300 millivolts across the plates of this capacitor. So definitely not zero. And also positive potential corresponds to the top plate of this capacitor. One thing we can note is that this voltage value is very sensitive to the proximity of my hand. Okay, let's now check how we can use this system for measurements. As Easter was not a long time ago, I purchased some decorations. These seemed very fancy, and I took this plastic egg and dipped it into silicone. So now I have silicone coated egg. Let's see now how the system responds when I touch the plate, the top plate, with this material. And we first saw a spike to the negative direction, and then we get a new offset at the positive direction. And now we're at 2.6 volts. Let's do this for a few times more. This is by no means a precision setup. We have so many variables, so many effects coming from the environment, from the air humidity, so on. But what we are interested in are the trends and also the order of magnitude of the effect. So let's touch a few more times and choose different locations. Okay, and what we can observe is that after each touch by this silicone coated egg to this top plate, we see a huge drift of the offset to a new value. So the open circuit potential acquires a new, rather stable value after each and every touch by this silicone egg. Let's do it a few more times. Okay. Now we have touched this 1, 2, 3, 4, 5, 6 times, and we have acquired a voltage of 8.7 volts. Let's check the same thing with the egg without silicone coating. Shall we get the same result? Let's first pause the measurement, then short circuit the inputs, and resume our measurement. Now we get a stable value of 4 volts. Now let's touch with this non-silicone coated egg. We got a small spike to the upward direction, but no offset drift anymore. Let's touch a few more times. Again, a small spike to the upward direction, but no offset drift. Let's do it more times. And still a very little offset. So, where does this offset drift come from in case of a silicone coated egg? Let's analyze now our results, shall we? So, in 6 cycles, we moved from the starting point of 0.5 volts to the end value of approximately 8.7 volts. Which gives us approximately 1.36 volts per cycle per average. We do know that it's a capacitive system, so let's now calculate the amount of charge increased on this capacitor or device under test. The charge on a capacitor can be calculated as the product of its capacitance and voltage. And in our case, the capacitance is our device under test, which is our capacitor. But in addition, we have to take into account also our measurement device. But fortunately, we have a measurement device with extremely low input capacitance. But still, we write it here as well. Picofarads times this voltage which gives us 3.81 times 10 to the minus 10 coulombs, and which is approximately 0.38 nanocoulombs. We have this many nanocoulombs, but we can also express it in moles. For that, we employ the Faraday's constant. Let's do that. 3.81 10 to the minus 10 coulombs, and this divided by the Faraday constant, which is 9.6485 coulombs per mole, and this gives us 3.95 times 10 to the minus 15 mole of electrons. We don't need this anymore. We do know a bit about the geometry as well. When we touched the copper plate with our silicon-coated egg, I estimated the contact area. I touched this egg, which has a thin but uniform coating of silicon, to a glass and observed how much was the contact area. And the contact area, it was a bit elliptical, but I approximated to a circle with a diameter of 2 millimeters. This is very approximate, but close enough. This is area of contact, and this area of contact in case of a circular approximation is 3.16 times 10 to the minus second centimeter squared. And this was in touch with silicon. Let's make a calculation on copper side. We do know the copper surface's lattice constant. Let's approximate it to a square. So the copper lattice constant is 3.6 angstroms. And in the square approximation, the contact area, this is A copper, the contact area will be equal to 1.307 times 10 to the minus 15 square centimeters. By dividing these values, we can estimate how many copper atoms were at the contact. But we can estimate it also in moles. So we have to further divide it by the Avogadro constant, which is 6.02 times 10 to the minus 20, sorry, plus 23 per mole. And the result of this one is 4.02 times 10 to the minus 11 moles. Great! To calculate how many copper atoms received an electron on average, we can just divide these values. So it's 3.95 times 10 to the minus 15 moles of electrons divided by 4.02 times 10 to the minus 11 moles of copper atoms. We get 0.98 times 10 to the minus 4 without a unit. We can estimate that one copper atom out of approximately 10,000 exchanged an electron in this touch event. An exchange of electron is the only feasible explanation for this charge generation. Some charge appeared. Now, let's discuss the fundamentals of this interaction we saw in this experiment. There are two major processes that occurred. One of these is electrostatic induction. And this was observed when I approached my hand to the capacitor plate, but also when I approach some other object. In this graph we can see that there is also a spike before the silicone egg touched the surface. So that part is electrostatic induction. Both the hand and also the silicone surface are charged. Approach to each other, they induce charge in the another. The other process is a triboelectric effect. And these both effects occur mostly simultaneously. What is a triboelectric effect? A triboelectricity is a fundamental property of all materials. All materials are characterized by their affinity to electrons. The affinity to electrons is described by a triboelectric series. And somewhere is a 0, and the more negative we go, the more electrons the surface gains. And the more positive side we go, the more the material rejects electrons. And where we are at with our materials? At the side of most negative materials available are PTFE, also Teflon, but also silicone. And one of the most positive materials available is a human hand, by surprise. Okay, we have found silicon, but where is copper? Copper is actually quite close to zero, but a tiny bit to the negative side. Let's further consider our system. We have copper, and on the other side we have our silicon on top of our Easter egg. We have copper that is slightly negative. And these negative signs means that surface of copper accepts electrons. So these are kind of voids or vacancies on the copper surface that are willing to accept electrons. On the other side, the silicon is very negative. That means it has lots of vacancies accepting electrons. Now, when these surfaces are approached to each other without touching, no electron transfer occurs, and we observe the electrostatic induction. So a charge with opposite polarity is induced on the other side, and this we can register as a change in our capacitor voltage, just as we saw in our experiment. Now let's take a look at the polarity. In our experiment, we observed that the potential at our top plate increased. What it means? After a contact event, some electrons from the copper surface were actually attracted to silicon surface. So that a decrease in electron density resulted in a positive potential on our electrode, just as expected. A triboelectric effect is often quantified as this kind of empirical series, where one material is left or right to another material. But of course there are many works that quantify this effect. And there was one which I recently found that gave a value for PDMS, which is in short for polydimethylsiloxane, which in turn is a chemical name for silicon. So that research paper measured this value for a silicon to be negative 100 microcoulombs per square meter. But now I'm giving you a task to compare this value from the literature to the values we measured in our very simple, very trivial experiment. As we remember, at each contact event between the silicon-coated egg and the copper surface generated on average 0.38 nanocoulombs of charge. It would be really interesting to find out whether this value was close to the value given in the literature. No measurement instrument in the world is good for each and every task. So let's revisit the choice of an instrument. The measurement performed in our experiment was a very special one. That was measurement of an open circuit potential. That means our device under test, our capacitor, had extremely high impedance. And instrumentally, it's rather demanding. But it has a lot of significance in bioengineering related applications. but I will come back to that a bit later. But before that, I would like to return to our choice of instruments. We notice that our oscilloscope as well as our multimeter were unable to measure the open circuit potential on our capacitor, that is our device under test, because any charge generated by the triboelectric effect would be very quickly diminished in this internal resistance of our measurement unit. Instead, our electrochemical measurement station was able to perform this measurement very easily. Because it had extremely high input impedance, we also have to take into account the cost efficiency of such approach. Also, the instrument was rather expensive. By no means I'm trying to give you an impression that for measurement of open circuit potential correctly, you certainly need to have this kind of electrochemical workstation. Remember, one of our goals of these labs was to give you guidelines of choosing the most appropriate instrument for your measurement needs. So I'm giving you another alternative in case you only need to perform this very experiment. And in particular, I'm adding one more instrument to our list. This is called an instrumentation amplifier, and the particular model is INA116, and this was manufactured by Brown. This kind of device is designed specifically for high impedance inputs, and it's not surprising to find out also its properties in the datasheet are very appropriate for that. So let's compare these values to our previous three instruments, shall we? So the input impedance of this instrumentation amplifier is characterized actually not very precisely. It is only said it is more than 10 to the 15 ohms. It is really challenging actually to characterize this kind of impedance properly. So 10 to the 15 ohms is actually 1 peta ohm. Have you used the prefix peta before? And the input capacitance of this instrument is ta-da! 0.2 picofarads. For this very specific type of measurement, a dedicated instrumental amplifier can actually perform better than the advanced electrochemical workstation. And how does it look like? Well, it has been on my table for a long time. So it's this chip in the middle. Shall we test it out? Of course! Now we have connected our instrumentation amplifier here to the oscilloscope as well as to the multimeter. The inputs of this amplifier connect to our parallel plate capacitor. This is all hooked up, and we don't have to worry anymore about the internal impedance of these instruments because of this preamplifier. So all that matters for this measurement is the input impedance of this amplifier. Let's test this circuit out with our Easter egg that is coated with silicone. Initially we see that the voltage is negative 0.3 approximately, and when we approach our silicone coated egg, we can see that our reading is extremely sensitive to the proximity to the egg. This is due to electrostatic induction, as explained previously. We can see that it's really sensitive to the proximity. But this is yet before touching. Let's now touch the sensor as before. Initially, the multimeter reads 0.3 volts. And we do a touch, now it reads 2.7 volts. Let's do it again. Now it reads 4.1 volts. Let's do it one more time. Now it reads 5.2 volts. So the values are a bit spread out, but in the very same range as we acquired using our electrochemical workstation before. And now you may wonder that such a preamplifier with these wonderful figures here must be extremely expensive. Well, you may be surprised or no, but the cost of this particular amplifier is currently at 17 euros. Again, as the aim of these labs was to guide you in choosing the most efficient setup for your measurement, and in case your measurement is measurement of open circuit voltage, then which instrument will you choose? Of course, you can make the experiment very nicely with a universal instrument, that is the Bioengineering electrochemical workstation. It can do a lot more than this task, but definitely in case you would need to measure the charge, this definitely does the trick. In case you would like to measure open circuit voltage using an oscilloscope or a multimeter, you will probably run into some problems due to the low internal resistance. But considering the setup, which includes the instrumentation amplifier as the preamplifier and the multimeter as the readout, then probably you have one of the best setups possible for this particular type of measurement. And it costs only 117 euros. So why we needed to have this preamplifier? Did it amplify the voltage? No. Did it amplify the current? No. The only reason of adding the preamplifier was to increase the input impedance of the measurement instrument, so as to enable measurement of very high impedance inputs. Let's now recall that the topic of these labs was mechanoelectric measurements. So how to convert a mechanical input into an electrical output. Of course, we have a lot of commercial sensors available in many different forms, using many different principles, also different material level properties. Also, we have available some in-house developed materials that convert mechanical bending into an electric output. But here in these labs I wanted to show you something more simple and more elegant. Here's the same setup we had before, the Bohr-Brown instrumental amplifier as the preamplifier. To the input of our preamplifier we have connected a common cable that is normally used for the oscilloscopes. And on the screen we can see that bending of this cable directly converts into a voltage using the Triboelectric effect. Well, this is not surprising considering that I've chosen the kind of cable that has a Teflon cover. To construct a mechanoelectric sensor, we don't have to actually connect any additional sensor to our cable, but we can use the intrinsic material properties of the insulating material inside the cable to convert the bending into an electrical signal. Let's try to twist it even further. We can observe that different kinds of mechanical stimulation directly result in a different voltage reading. And this is due to the friction between the insulating material and the core conductor. So a triboelectric effect occurs when the inner conductor is sliding in reference to the insulating material surrounding this. And as we are capable of directly quantifying this charge that is generated from this friction, that is the triboelectric effect, we can construct the simplest mechanoelectric sensor just using a piece of cable. And one more thing, the material that was used as a dielectric in this cable is Teflon. And on the Triboelectric series we saw that Teflon together with the silicon was one of the most left on this Triboelectric series. That means the highest effect in contact with copper, that is also the inner core of this cable. In our previous demonstration we saw that the simple cable can generate a lot of electrical charge upon just mechanical bending. In this case we considered it as useful because we wanted to convert a mechanical input to an electrical output, as was the task in these labs. We can observe that the multimeters, like this one, are commonly supplied with very nicely behaving silicon covered cables that are really nice to work with, but as we previously saw, a silicon is extremely active mechanoelectrically. So in case we would like to make precision open circuit voltage measurements or measurement of devices with extremely high impedance, we quickly run into trouble with the silicon cables like that. But let's see which kind of cables are used in the electrochemical workstation. Well, definitely they are not silicon or Teflon, because those materials will be way too electromechanically active. One take-home message from these labs is that the voltage measurement, which initially seemed so simple task, just take a multimeter and that's it, can be a really involved process in case really small currents and high impedances are involved. I would also like to introduce you some terminology. From the voltmeters, a special category is designated for high impedance solutions, and those voltmeters are called electrometers. And both the electrochemical workstation as well as the Burr-Brown instrumentation amplifier we used can be considered as electrometers. The electrometers, such as inside the front-end amplifier for this electrochemical workstation, as well as this instrumentation amplifier we used, are designed for the highest input impedance. That means they generate the minimum amount of electrical current themselves, so as to allow measurement of extremely high impedance sources. Another important take-home message from these labs is that we employed the electronic properties of an insulating material, that is silicon. But how is these labs actually relevant to the bioengineering field? In this case, we just demonstrated a very simple configuration. We converted a mechanical input, that is motion or touch, into an electrical signal that can be registered and measured very easily. But the same principles actually apply to many different applications in bioengineering field. For example, let's consider a sensor that is a conductive surface that has an antigen bound on the surface. This antigen can bind to different antibodies from the environment. We know that both these antigens and antibodies are materials, so it is very likely that they will also have their designated place in the triboelectric series. So the same principles as we use today could be used to construct a new generation of a biosensor. Let's consider once more the ranges. We saw that even a small touch by the silicon-coated egg almost saturated the input of our electrometer in our electrochemical workstation. That means we are nowhere near the capabilities. We can measure way smaller charges from way more intricate processes. But the principles of signal conversion from a mechanical input to electrical output is very similar. The third take-home message from these labs is that most materials around us are mechanoelectrically active. Although our demonstration was extremely simple, we just used some Easter decorations covered with silicone, we actually perform something that is extremely intrinsic at the material level. We performed atomic level charge separation between different materials, one of which was even insulating material. I hope this lab gave you some guidelines for designing your measurements and choosing the most suitable instrument for performing electrical measurements in your application. And also remember, even such a simple task as choosing a voltmeter can be a really tedious task and take a lot of your working time. Hopefully not as much time as my hair has grown during this pandemic season. Thank you very much for listening. I'm always available for questions and comments, and I'm hoping to see you soon.